Welcome back to ECE 320A. In this video in Unit 11, we want to talk about where in fact these poles are located, or what's their pattern when they are associated with a Butterworth filter. Or what can we say if somebody says, I want my filter to have a Butterworth behavior or a Butterworth characteristics, then what does that mean, and where are those poles located relative to each other, or what is the pattern of these poles when we talk about Butterworth filters? To begin with, let's just try to quickly summarize some of the key features of Butterworth filters. One is, and I like to refer to this as what is really flat that you have for breakfast, or you might hear somebody said, oh, it's flatter than a pancake. Well, what do you put on those pancakes? You may put some syrup on those, and so now you have this Butterworth syrup brand. No real plug or advertising. I'm not getting any royalties for that plug, but it might help you remember that when you're talking about a Butterworth filter, the magnitude is maximally flat in the passband, which means that the derivatives of the magnitude squared of the transfer function, those derivatives equal 0 at DC. And how many? Well, 2n minus 1 of those derivatives for an nth order filter actually are equal to 0 in this Butterworth filter. So the magnitude in the passband is maximally flat. And maximally flat means that these derivatives, or this slope essentially of the magnitude response, is not very, it doesn't change by very much. Also, the magnitude is monotonic in both the pass band and the stop band. If we looked at these magnitude responses in an absolute scale, then you can see that there's no up and down movement in the pass band on the left in that picture, or there's no up and down movement in the magnitude response in the stop band, as compared with the response on the right, where we might have some mins and maxes, some wiggling in the pass band, and we might have some wiggling in the stop band. And why might we have those? Well, those might actually lead to a sharper transition at the cutoff, so we might be able to roll off more rapidly if we tolerate some up and down magnitude behavior in the pass band and or the stop band. And you can have filters that maybe have ripple in the pass band and not in the stop band, maybe in the stop band and not in the pass band, or maybe the ripple is in both. In the Butterworth filter, we have this monotonic behavior, so it's just gradually in the pass band rolling off, and then it rolls off into the stop band, maybe more dramatically, but it doesn't go up and down in either the pass band or the stop band. The magnitude changes monotonically in a Butterworth filter. Another key feature of the Butterworth is that its magnitude response actually has this magnitude characteristic as a function of frequency. It's 1 over the square root of 1 plus the quantity omega over omega sub c raised to the 2n. And that's now what the magnitude response looks like for a Butterworth filter, and that's what leads to this maximally flat behavior, and this is for an nth order filter. These Butterworth pole patterns, then, if you look at them, or you can check table 15.1, and let me just scroll quickly down to table 15.1, you can see that the constants in all of these factors in the first row, that's a first order pole factor. In the second row, that's a second order. but each constant in those factors is 1. So this is now a normalized, these have been normalized to have a bandwidth of omega sub c equal to 1 radian per second. Or said another way, all of the poles are equidistant from the origin, and that equidistance is a value of 1 away from the origin. So their natural frequency, this hypotenuse of the pole locations, is 1 away, or is a distance of 1 in these normalized Butterworth polynomials from the origin. And that's because of all of these constants having a value of 1 in their factored form. What's different now in these different parameterizations, each row corresponds to a higher order polynomial, but now you can see that these linear factors obviously have different values in even within the same nth order filter. So for n equal 4, B1 in the first factor is 0.765 and B1 in the second factor is 1.848. Now what does all of this mean? Well, all of that actually means something about, and here's where I'm hoping you can start to gain some insight into what's happening. Let's look at what happens when we have a first order filter. Then the denominator is this s plus 1. It's normalized to 1. And where's the pole? The pole is the value of s that satisfies that. It's at minus 1. Well, if we think of that a little bit differently, this middle column says what's the angular separation between the poles? And now what we're going to do is we're actually going to have poles that are mirror images of each other across the imaginary axis, but in the Butterworth filters that we will design, the low pass, we're only going to worry about stable pole locations, so we're going to discard all of the poles in the right half plane. We're only going to keep the stable poles. Now, if we think of n, little n being our filter order, and we say we have a first order filter, then in this picture of doubled poles, then we have 360 divided by 2 times n. N is 1, so there's an angle or an angular separation between those two poles of 180 degrees. That's this angle, or that's this angle. They're separated by 180 degrees. So if you now know that you have one pole, it's odd, and it's a distance of 1 away from the origin, and its twin in the right half plane, or its mirror image, is 180 degrees away, there's only really one pattern that matches those particular conditions or constraints. Let's now up the order to a factor of 2. Now if we look at this angular separation formula, 360 divided by 2n, if we divide 360 by 4, then that gives us 90 degrees. Well, if we have 90 degrees of separation, then there's a few different ways that we could rotate that, but we need these poles to 1 give us 2 in the left half plane, and they have to be now separated by 90 degrees from each other. So in this case, these poles are 90 degrees apart. These are 90 degrees apart. Those poles, one of those cannot be on the real line, because then we would have 2 on the imaginary axis and 1 on the positive real line. We would have 4 poles, but we wouldn't have 2 that were purely stable. In order to be purely stable, then we have to have these 2 poles offset from the real axis, and that real axis now divides their angle in half. So half of the 90 degrees is up, 45 and half is down, there's our 90 degrees. And what else do we know? We know that the constant is a value of 1, so they are 1 away from the origin. And if they're 1 away from the origin, then we know exactly where those are. We have the magnitude and we have the angle. We can find those locations. They're at minus 1 over the square root of 2 plus and minus j square root of 2. That's for n equal to 2. And now can you anticipate where those poles are going to be for n equal 3? Well, when we have an odd number, then one of those will be on the real axis. Just like in n equal to 1, we had one pole and it was right on the real axis. Now, for n equal to 3, the angular separation is 360 divided by 6, 60 degrees. So now these poles need to be separated by 60 degrees. One of those is on the real line. We go up 60 degrees from that, and we have one of our poles. We go down 60 degrees from that minus 1 location, and we have our second pole. And they are uniformly spaced, and they're mirror images in the complex S-plane, and they are 1 away from the origin, each one of these. And all we're doing now is, now that we have 6 poles, if we want a third order filter, we simply keep those poles that are in the left half plane. We want this filter to be stable. And now we know exactly where those poles are located. For what? This is our Butterworth pattern, and this now allows us to always cross a minus 3 dB point at an omega equal to 1. That's the beauty of these Butterworth pole patterns for our pole locations. If we go up to the next n equal to 4, now 4 is even. We won't have anything on the real line, but now they have to be in such a pattern that they are separated by 360 degrees divided by 8. So 360 divided by 4 is 90. We divide that by 2, we get 45. Now we have to split that 45 equally around the real line, and now we know what the first pole is just above the real axis in the left half plane. And then the next one is 45 from it. This one is 22.5 degrees down. This one's 45 from it. So that the aggregate angle between those two poles is twice 22.5 or 45 degrees. And again, we just keep the 4 poles that are in the left half plane. And those now, if you looked at those, you could calculate those locations, and you could in fact build those quadratics. We know we have one set that has a real part that's bigger. That's where this 1.8, so you divide that by 2. These must have a real part of 1.848 divided by 2. So they're at minus 0.9 something. And these, this one and that one, now have a real part that's half of that. So now they're at minus 0.38 something.